So welcoming you all again to this talk. We are from NVIDIA. I'm Smitha and my colleague Vinod. We'll be today talking about how we can achieve inferencing at scale and how the Kubernetes platform is really an ideal platform for us to achieve inferencing at scale. Let's move on. So today's content is pretty much about, ML inferencing. So from morning, we've heard a lot about different aspects of deploying, inferencing microservices. Some in terms of, we just had a talk on performance a little earlier. We had a talk on how to deploy, whether it should be a canary deployment or a blue-green deployment. I think morning we had another talk similarly. But what we are going to cover is slightly different. So bear with me. We are going to take an example of a RAG pipeline implementation and show how that can actually scale on Kubernetes using GPUs. So that will be achieved through our NVIDIA GPU ecosystem on Kubernetes. We'll introduce you to NVIDIA Inferencing Microservices and a little bit about how they are different from what is available in open source, like Llama 3 or Mistral or whatever we already have. What is the difference between those models and what we say as NVIDIA inference optimized inferencing microservices. We'll talk about the pipeline. Basically, it's not just one inferencing engine that will help you achieve any complex business use case. We'll have to basically deploy a set of inferencing services to achieve what we want to do. So how do we pipeline that? How do we deploy them together and make it work? And building a RAG. A RAG is essentially a retrieval augmented generator. It's an example of a generative AI where, at the end of it, you'll really be seeing how you can quickly and efficiently deploy a simple chatbot for your business needs. Of course, making it production ready is another story, right? Downloading an open source model and running it on a GPU and making it work is trivial. But when we want to host it on production, what are the challenges we face? So there we look at metrics, auto-scaling, monitoring, and a short demo of whatever we've spoken about so far. So ML, right? Last few years, it was pretty much in a POC stage where there was a lot of work and emphasis on training that happened. So training is sort of what happens at the back end, or what you call as a development phase in an ML life cycle, right? You keep training a model, you need a lot of resources, you need a lot of time to train a model, and so on and so forth, cost and everything. But what happens at the end of that, right? You are ready to deploy your trained model into production for actual use. So that's where we are today at the cusp of 2024 or 5 that we are entering. We actually want to deploy our trained models on production for real life use cases. So we are there, and how we want to achieve this is what we'll see today. Okay, there are 2 ways in which we can deploy these inferencing services to achieve our production grade or enterprise grade metrics. So one is we can scale them up. So you can have multiple inferencing services that cater to one set of queries or prompts, or you will have to pipeline different set of microservices to achieve what we call as a pipeline. So we'll look at both of these things today. So coming to the production phase, right? What exactly are the challenges? So how do we actually deploy these generative AI models? What does it involve in it, right? So you can see, let me go in a clockwise manner over here. So just like any other microservice that has to get into production, first thing is about safety of user data. Let's say I'm an enterprise and I want to host a chatbot, but which serves my own custom business needs, and I have my own data that I want to train the chatbot on. Now, I don't want to go take it to a generative AI or a Google Gemini and say, okay, this is my data, please train it for my use case. So that defeats the purpose of my own proprietariness in the data, right? So one is security of data. Second is how relevant the chatbot responses are for my queries. So that's what we call as LLM hallucinations, right? We want to minimize LLM hallucinations as much as possible. And then it's about performance and latency, throughput and latency. How many queries per second or minute can my bot handle? Or how many images can can I do inferencing on per second or per minute? So there are these enterprise level metrics that I want to achieve. So if I have such goals, how do I do it? It's like working backwards, right? And of course, finally, it's all about effective utilization of resources. So I think through the day, we've been seeing how well to utilize a GPU or how well to utilize a fabric bandwidth, etc. So to do this, right, we can sort of do it in two ways. One is we can take our use case and go to a managed hosted inferencing service like I was saying, right? We can use ChatGPT to train the data we want to do or inference the data, but that's not what we want. So what we want to do is we want to tell you how you can deploy your own microservice in a cloud or in your on-prem itself and still achieve enterprise level inferencing. So I'll hand it over to Vinod to sort of walk you through what we have at NVIDIA in this.
Good evening, everybody, and welcome again. Thanks, Smitha, for this context. Am I audible? Okay. And how many of you are here ML practitioners? Okay, good. I think most of this will be relevant, and we'll not go deep into the nuts and bolts of what is being done, but we will try to cover it so that the main idea that we want to convey here is how to build an ML inferencing service using Kubernetes and also leveraging some of the NVIDIA specific software stack. Of course, to run on NVIDIA GPU as well as other GPUs. Okay. So now, as Smitha said, we will try to take LLM as an example, and LLM also, the text part of LLM, not the speech and vision. That is just for the description and the problem statement today, right? So if you look at LLM, right, large language model are by and large auto-regressive models, right? Because what you predict next is going to be lotly depending on what has been the input prompt and the prediction so far. So that's why these models are mostly auto-regressive, and there's a lot of computation required in the prediction. And when you want to deploy it at scale, you have to understand the dynamics of the internal inferencing engine so that you can actually see what do I need. Is my inferencing model working good? If my inferencing system sufficient to cater to the needs that I have? And how do I look at the observability standpoint, right? Both from performance as well as utilization. So that's what we look at. So this slide is just to give that example. Now, before you go into the details of Kubernetes and how ML inferencing is related, I'm sure this is mostly known to everyone, but people who are not ML practitioners, we just thought we'll cover it. As we said, AI ML needs a lot of resources, and the resources have to come from a cluster, and that has to be well orchestrated. And by now, we all know Kubernetes is a good orchestration engine for a cluster, right? Be in terms of CPU, memory, and specialized resources like network and GPU, right? Now, that is where GPU comes in, because Kubernetes has a good management capability for all the native resources, right? Be it CPU, be it memory, be it network, right? You have a lot of software stack around it. Does it have a good software stack mechanism to identify the non-native resources, what we call GPUs, right? Or specialized infinite band controllers? No. That is where the software stack from companies like NVIDIA come, where they build software stack to make the GPU as a first-class citizen in Kubernetes, right? Through the operators, through the device plugins, through the feature discovery, daemons, etc. Right? So we'll see that how we are developing that and how we are building up the ecosystem. And last is, as I said, AI/ML and Kubernetes goes a long way. Machine learning and GPU goes a long way. That means GPU and Kubernetes goes a long way, right? That is the context of our discussion. Now, as I talked about, how do we make the GPUs, the non-native resources, right, the specialized resources, an important and first-class citizen in Kubernetes ecosystem? And that is mostly developed using this operator framework. And the operator framework is important because I'm sure how many of you have used GPUs or specialized resources in Kubernetes, right? You have to ensure that you install the right drivers. And the entire lifecycle management of the driver and the resources is not easy, right? So that's where the operator comes in, right? You build the operator so that you have a GPU operator which takes care of what driver to be installed, right? What is the life cycle of the driver? How to upgrade it? How to find if the GPU health is bad? How to propagate that to your application and your telemetry data, etc. So that is where this GPU operator comes in, which has a GPU driver pod, a container runtime, device plugin. Device plugin is responsible for advertising the GPU to the Kubernetes cluster, your kubelet, and also your scheduler, so that he can know, okay, this node has the specialized GPUs, I can allocate job to it, I can schedule job, etc. Right? So that's where the GPU operator comes in by and large. Similarly, as we know, right, when training and inferencing, one GPU is not going to do the job, or one node is not going to do the job. You need a cluster of them, right? So how do you connect the GPUs in a way which can scale? I think slightly after lunch, there was a talk from, I think it's Red Hat, right? They talked about how they build multi-GPU training pipeline, right? And they used about ROC, Rocky, InfiniBand. Now, how does that communication work, right? How do you ensure that the GPU can transfer data at scale, right, without adding latency? That is where we bring the network operator. How will you give a secondary network to your Kubernetes stack? And the secondary network, either using Rocky or InfiniBand or any specialized network, right? How do you ensure that the GPU can transfer data through that in a faster way? So these two operators, these are the two engines I would call of your any ML, be in training or inferencing engine. Now, having said that, now we said the inferencing engines are going to be built and run as microservices, right? Now, do we want developers to create their own microservices and put time and effort? No. That is where the NVIDIA's inferencing microservices, short-term NIM, comes in, where, as you know, right, if you want to really use a GPU, as I said, you need a stack of GPU operator, a network operator, and you also need runtime, right, which actually gives the GPU to your container, right? Because be it containerd, Dockerd, they don't look at GPU and say, okay, how do I pass in the GPU as a visible resource to the container, right? That's not done. You need a specialized software stack called container runtime. Now, and then after that, you need to ensure you have the right model, you have the right inferencing engine, and you need the right model for the right GPU you have. That's a complexity, right? That complexity is what being avoided by building NIMs, which is NVIDIA Inferencing Microservices, which allows you to just take the NIM, put it on your hardware. The NIM will automatically detect what kind of hardware you have, what is the capability of the hardware in terms of compute and memory, and what driver required, what model will be run there, etc. Right? So that's what NIM is about. And basically, it is to give you improved TCO, day zero support, and also simplify your development. Right? That's what NIM is about. Now, by looking inside, right, what is NIM? Just like talk about, NIM can run on either cloud, or it can run on a data center, or it can run on your data center server, or you can run on your laptop or a workstation, right? That is what fundamentally we want the NIM, the microservice, run on any infrastructure. On top of that, what you need, I'm sure who are familiar with the GPU acceleration library, which is CUDA for us, or if for that matter, any acceleration engine. And on top of that, you have Kubernetes. As I said, all the GPU operator and the cloud native stack that actually exposes the GPU to the operating system or the container. And on top of that, you have the inferencing engine. It can be the standard APIs, which is catering to a text, speech, or vision. right, which we call as Open API. And on the left side, you have the secret sauce which comes in, right, which is about how do you specify which model to use, because each model is depending on, okay, this model is faster on this GPU. And for this model, I need this inferencing engine, maybe TensorRT or VLLM, so that for this hardware, it is faster. So that complexity is all hidden and abstracted in NIMs, so that developers don't have to worry about, oh, I need to take this model, and I'm going to run it on this hardware, so what combination I need, that is what's being avoided. Right? That's why it is a prepackaged microservice. The theory of operation, basically how NIM works is when you download a NIM, run it on your system as a container, actually it detects the hardware which is running on, which I told already, mounts the required cache model, right? I mean, pulling the model always from a repository is going to be hard. So you have a NIM cache so that you can always load your model. That gives you a good time about your microservice start time, or what we call as the time to first token. We will see that in an example. And also select the most optimal model given the hardware, and downloads the model from our cloud or any cloud or repo that you can point it to, and loads the model and starts serving. So basically, how to ensure that the microservice starts serving model, what you want. Now, one problem which I talked about the optimization. We have two things. One is, how do you optimize your hardware? Second is, how speed is your AI system, right, in terms of inferencing? How many services how many requests it can do, how many tokens it can generate per second, and also what is the throughput, right, and latency. So that is what we are trying to avoid by saying it's a combinatorial problem. It's a combinatorial optimization problem based on these parameters. What kind of GPUs you have, right? How many GPUs you have per node? What is the throughput that you want from a latency and, what's the performance indication that you have from a latency and throughput point of view? And what is the precision value you want, right? So based on all these, you can select which model you want to run. And that is where the optimization overhead is removed from a developer or a system admin who is deploying this to ensure that the NIM will automatically detect it. It uses this, the intelligence that it has, and decides which model is required for you to run, right? So that's about NIMs. Now, we talked about Kubernetes. We talked about how do this GPUs are exposed to containers, right, using this cloud-native software stack, which we may say. And we also told what NIMs is, right? NIMs is the optimized microservice inferencing engine. Now, our whole discussion today, now next 10-15 minutes, is going to be how do you build a working inferencing AI system, right, using these small bits and pieces. Now, to start that, to set a stage for that, your idea is, okay, you want to have a generative AI system, right, and you want to use an LLM. Maybe, let's say, text will be our sample for today. Now, the key capability of generative AI doesn't depend on only one NIM service, right? You need multiple of them. And why do you need multiple of them? Because you need one for transforming your data, one for doing the actual generation, and then you need something for re-ranking, because you need to ensure the data is appropriate for your context. And then you also need security guardrails, right? So that these data, or the inferencing token that is going out, is not inappropriate for your content. It also doesn't leak any of the operations. So you need a lot of guardrails in the system. So, and each of them is another AI model, another AI engine, another AI microservice. So that is where we said one NIM is not enough. You need an army of NIM to ensure that your AI system is in place, right? So to illustrate that, and then also to see how you can quickly develop and deploy that in Kubernetes, we'll have a demo also. Now, we will take a text-based RAG as an example, right? RAG stands for Retriever Augmentation Generation, right? So RAG is retrieve, augment, and generate. So what do you mean by retrieve, right? So these are the two aspects of RAG, right? Or any text-based LLM engine, right? One is you have a lot of external data. You put that to an embedding model, then you have an LLM, right? Which is what we call as the large language model from either Meta, right, or from Mistral, right? So you have an LLM. Now, to that LLM, you give any input token or any query that's going to generate something, right? And like Smitha said, if that data is not relevant for your domain or your company's need, LLM will generate something which is he thinks is right, which is we call it hallucination, right? To avoid that, always you need to give your private data source. And the private data also goes in the same model. It goes to an embedding model, it goes to a vector DB, and based on the query, the corresponding vector DB content will be retrieved. And that is what is passed into LLM to give you the context-based inferencing token. So that's how we build context into the large language models. Next slide, please. Now, this is another, I would say, the theory of operation, what we call the flow model of how the data, right? How the data pass through this, right? So you have Llama index or maybe LangChain, right? That is the orchestration engine. And that sends the documents to your embedding model. Embedding model sends it to vector DB after creating the embeds. And then the vector DB content is what is going to the LLM, right? Your LLM. And based on user query, what happens is the queries also are embedded and goes into the vector DB so that, as I said, the auto-regressiveness, right? Because the query also depends on what exactly going to be the token I'm going to produce, right? So that's what this model is. Now, what I said is we need multiple microservices, be it LLM model, be it an embedding engine, be it a retriever engine. All these are microservices. And you need all of them to work together, all of them to scale together to ensure your AI system is appropriate. Now, that problem is not very simple because, as I said, this is another way. For each of that, right, what you call the Meta or the Mistral model, we call them as foundation model, right? And the foundation model itself, you have multiple of them to decide, right, which one to use. Similarly, for text embedding, you have multiple of them. For vector data database, there are multiple open source or enterprise vector data database today. And for the data framework for LLMs, you have again LangChain or Llama index, right? One more click, please. Yeah. So this is the problem space what we are trying to solve, right? Because, as I said, any generative AI system needs multiple microservices, and each of them you have thousands of options. Now, how do you ensure that you can quickly deploy this and generate and create an AI system by yourself? I think that's going to be our next phase of discussion and demo.
Yeah, thanks, Vinod. So whatever theory that we heard from Vinod, right, today we'll now look at sort of how do you deploy them in practice. So the next 10 minutes is probably we're going to cover that before the demo. So you can correlate each of these layers to whatever we have discussed so far. So basically the lowest layer is the infrastructure, which is the GPU and the various operators that are required to make GPU available to the NIM pods or the inferencing pods. Then we have this PVC or a storage class simply to cache the model data. We don't want to keep fetching the model data every time a prompt is received. So we require a PVC for that. The NIM itself is packaged in a very neat way, and it's just pull and deploy. And then the NIM exposes itself through a service called as a LLM service. And that, of course, you can use an ingress or not use an ingress, depending. So this is a very simplistic picture of how a single inferencing engine can be deployed. Now, let's look at how we can chain them, because one is not enough. Just like he was saying, we need one for embedding, we need one for re-ranking, probably we need multiple such. So the beauty of this Kubernetes-based deployment is you can add any number of verticals like this. For example, your front end and your chain service. And then that, all of these independent inferencing services are chained in this manner using the chaining server. How do we do that, right? Through Helm charts, of course, but there are two ways to do it. One is a simple Helm deploy, and then you can deploy each of those vertical blocks that we saw separately. We can pull the Helm chart and deploy them and ensure that they're all working together. Or we can use a NIM operator. So this is really the one-click way of deploying a RAG pipeline, because this makes sure that all of those components are there, their dependencies are taken care of, they are talking to each other, their health is good, they send out the right metrics, they scale in the right way, etc., etc. So NIM operator is a very, it makes our life really easy to deploy a pipeline. So you can see there are 3 kinds of custom resources that the operator watches for. That is the NIM cache. That is nothing but the PVC that gets generated for, that gets created for a inferencing engine. The NIM service itself, because the NIM OpenAPI server is exposed through the NIM service, and the NIM pipeline. That is a combination of these services is called as a pipeline. So you can manage the pipeline as a whole. You don't have to worry about scaling each and every of one of those services individually. You can manage them as a unit as the number of input queries increase. So, this sort of gives you a picture of what happens when you have a heterogeneous set of nodes in the cluster. So, let's say I have, when I say heterogeneous, it means I may have a node with 2 GPUs, a node with H100 type of Hopper GPUs or Ampere GPUs or L40s. So, the NIM automatically, by virtue of detecting the hardware, knows which model to download, knows what is the capability of the underlying hardware, and everything is automatically handled. The admin doesn't have to worry about it. Other thing is the access control is very much governed by the Kubernetes RBAC infrastructure. So there is really no security issue there as far as deployment of the inferencing engine is concerned. So one of the most important aspects of productizing is monitoring and auto-scaling. And Prometheus is, of course, our favorite monitoring solution. It's an open source server. This is really nothing to do with NVIDIA, but this is just like, I thought it brings in the concept of what Prometheus is and how it can monitor the various services. This is a very important slide. So monitoring comes in 2 aspects when you think of LLMs, right? One is monitoring of the hardware itself, utilization of the hardware, because we know, right, GPUs are very expensive resources. So how well am I utilizing that is very important. And the NIM itself, how many requests per minute am I able to handle? What is my time to generate the first token? What is my inter-token latency, etc.? So there are 2 aspects to monitoring. The first one is our data center GPU manager that is deployed as part of the GPU operator itself. So you don't have to do anything extra. The GPU operator itself will deploy this exporter, and the Prometheus can scrape from that exporter automatically. Now, we'll keep coming back to this deployment diagram. We'll keep adding pillars into this to finally build our chain. Now we have actually added our Prometheus stack or the monitoring stack as well into this. Let's move on. So the second part of monitoring, I said, right? How is the NIM service itself monitored? Because, based on how well the NIM is performing, you'll know whether you're reaching your business goal or not. For example, right, like let's say I want to develop a chatbot which serves, let's say about 15 requests per second, and I want the I want the first token to be generated in no less than 3 seconds. So I can have SLAs like this when I want to size up my RAG application. Because eventually user experience is what counts. And we can't have it take forever to produce the result. If I say, okay, like how I'll be showing in my demo, what is the weather in Delhi? If I say, I really need to see it immediately. If I have to wait for 1 minute, then probably then the whole point is lost. So really to achieve that level of quickness and agility, we have to monitor the service. The NIM service monitor helps there. So the NIM service monitor, as you can see, basically says which label name I have to match in order for Prometheus to start scraping that metrics from there. So ultimately, Prometheus is the one who scrapes the metrics from the NIM service, but then how does it know what to do is what the NIM monitoring service helps in. This is a very important slide. So NIMS really provides many metrics. Few of these are listed here. So in terms of KV cache is basically GPU memory utilization. Okay, and then count. Count is, of course, how many am I currently concurrently running, what is the waiting count, what is the max request, etc. Then latency, which is really very important, because time to first token generation is what is like TTL. TTFT is the one that really determines how optimized your inferencing engine is. Total time to generation is another one, because it measures end-to-end the total time taken to process my input prompt to generate the output tokens. So that also must be in the order of seconds, that too less than 10 seconds. And then inter-token latency is another thing. So because we are auto-regressive, right? Every time I generate a token, that token gets fed back into the system and the next token gets generated. So what is the time taken for that auto-regressive mechanism to work is what determines the inter-token latency. Of course, since we are exposing metrics through Prometheus, Grafana is a very good tool for you to visualize and create an observability chart with each of those, as you can see, the metrics that we just talked about. Lastly, we'll talk about auto-scaling a bit, because ultimately, when you have to run something in production, it has to be scaled up or down. Not only for user experience, but also to make sure our resources are efficiently utilized. Basically, here we can do a horizontal pod autoscale for the NIM microservice, so that basically the HPA will increase or decrease the replica set count based on the custom metrics that it fetches from the Prometheus adapter. The Prometheus adapter itself fetches it from the operator. So it's like a feedback loop. We can create an HPA. Maybe the next slide. Yeah, so this is an example of a horizontal pod autoscaler where we are saying we want min replicas as 1, max as 2, and for this deployment, watch for the metric called GPU average utilization. And if the average utilization exceeds 30%, go ahead and scale it to 2 replicas. So this is the directive that is given to the HPA. HPA will watch on the Prometheus adapter and implement the replica upscale or downscale. Here, let me pause. We'll show you exactly whatever we spoke about till so far. The first 1 minute of this video, the video itself is about 4 minutes, so maybe the first one and a half minutes talks about the operator, how the operator creates the various custom resources. For example, this is a 3-node cluster, and we have an NFS as the storage client, because for my PVC, the inferencing caching, we needed a PVC. So we just installed the operator created the CRDs, and now we'll create custom resources for NIM cache, okay, first, and then the NIM service itself. You see now the NIM service is getting created, and it is now ready. So if we can pause here, right? So you see there are 2 inferencing microservices that we are trying to chain and pipeline here. So we need the front end and the chaining server, which we will come to. So this is first half of the infrastructure that is already ready. Now we see that the NIM service is created. We'll take the service IP of the NIM service. Yeah, so it is now ready. We can annotate it so that Prometheus scrapes from it. And then we are ready to actually deploy the front end or the chain server after this. So yes, so this is how a NIM service looks like. We have a cluster IP, and 8000 is the port where the OpenAPI server listens on. We'll have to, this is part of the application deployment. We need a Milvus database, so we have created a Milvus service with a cluster IP and 19530 is the default port for Milvis. So we'll port forward the Milvis service, and now we'll deploy a RAG sample application. That RAG sample application itself is a service, because that's what is the front-end service that will be exposed on the node port on this particular port. So we can go to a browser. If you see, that's the node port address. And this is what comes up. So this is really quick, right? In a matter of minutes, you can actually deploy your own sample chatbot like this, which will actually not only give you the query, but it'll also use embedding and retrieval to make your query more contextual. So we can see now that we've asked a sample question, what's the weather in Delhi? I thought that's the most relevant thing people will care about in today's session. So it just gave me, a generic response saying, okay, this is what the temperature in Delhi is, and this is how it is, and stuff like that. But that's not, that's not enough for me. I want it to be more contextual. So we just uploaded a document saying, okay, this is the Delhi weather in June is so-and-so. So this is that other domain-specific information that you will be providing, saying that weather is a generic information, weather in June is my domain-specific information, and eventually the response, if I ask again, what is the weather in Delhi, you're going to get a better answer, a more fine-tuned answer to the same question. So that's the power of creating it as a pipeline versus just downloading a llama and then saying that I have created an LLM. So for it to be contextual and for it to be more accurate, you need to supplement it with some additional information and deploy it as a pipeline. So yeah, this we can walk through quickly. This is how the Grafana chart looks like for my sample application. And we'll now try to scale this, okay? We had a single replica, right? The pod, we had a single pod basically that was running Llama. Now we will look at see, the replicas are 1 and max are 2. So this is the HPA advice that I've said that, okay, look at the number of requests that are coming in. If the number of requests exceeds 5, go ahead and do the auto scaling. So you'll see that we wrote up a script which will keep sending multiple queries at the same time. And if you see, the number of pods will eventually increase from 1 to 2 and so on. So you see there are 3 pods now, and we are now sending more requests. Okay. Instead of the UI, this is just doing it through the shell. That's the only difference. And now you can see the max request has gone to 5 and 10. So number of pods became 4. So this is how simple it is to actually scale and monitor and do the scaling for a RAG pipeline. That was pretty much the gist of our talk. I think Vinod will conclude, and then we'll take up any questions if you have.
Take 1 more minute. I think just to conclude, this is what we tried to achieve today. One is to talk about inferencing. Today it's the era of inferencing, right? 24, 25, 26 is going to be. And what is NIM? How is it going to help you in creating your inferencing AI system? How do you optimize, right, along with the K8s and the features of Kubernetes? How do you make it scalable and robust with all the monitoring facility, the microservices, scaling HPA, that entire collection of tools that we have, and then how easily to integrate this into your MLOps, right? So that's what we wanted to cover. Thank you, and any questions we can take now. Yes, please. Uh-huh. NVIDIA GPU. So today NIMS is going to have a front end, right, which is standard, right, the fast API based front end. But back end is talking to only NVIDIA GPU. So yeah, southbound part is today really tied to the hardware. But that's the best of both worlds, right? The front part anybody can use. Yeah. Right. So this is about how do you update the NIM, right? NIM microservice. That's all is baked into the NIM operator. So if you use NIM operator to install NIM, you can just make a change into update the NIM operator YAML file, and you say, okay, what NIM version I want is next. It will automatically pull and upgrade it. So you don't have to worry about it. It's just a matter of changing the operator YAML file. So the operator will take care of upgrading your NIMs. No, it won't. Just like you do any upgrade using operator. Sorry. Sorry.
You did mention that NIM can choose the model automatically. And how does that happen? Is it or does that work only with the model repository of NVIDIA, or can it work with any model repository?
Yeah, I think the question was that the NIM, when it chooses the model, does it work only with the model repository of NVIDIA or any model? So the answer is yes. It will work with the model repository of NVIDIA, but we also have the option of bringing your own model, and you have to just give a YAML file which says what model suited for what, and it'll automatically. So both, your own model. Yes, yes. Sorry.
So we were talking about the monitoring of how much GPU VRAM is being utilized, right? So I have seen constraints about how many cores are being utilized, whether it's CUDA core or the Tensor cores, right? So what is the way to monitor that? I was not able to find it out.
The question is how to you look at the GPU utilization, right? Now you are looking at the CUDA core or Tensor core. So that depends on which metrics are you using. Like, so we talked about DCGM exporter here. So DCGM exporter gives you counters at every level. So the GPU utilization is one counter, which is going to give you the gross utilization. If you want to look at either a CUDA core or a Tensor core, then you have sub counters for it. So I would say you should better use the GPU util as the metric. Then that will give you the overall utilization. If you're using CUDA core, then you may be missing on the encoder, decoder, etc. Right? So better to use GPU utilization as the one. GPU utilization and memory, right? The frame buffer utilization. Those are the two counters that you should use, so that you get a good view of what the GPU utilization is. Right? Not the tensor counters or CUDA count. That is to optimize your application as such, right? Am I utilizing my cores correctly? But when you want to put in production, those counters are not required or not important for you. What is important is the overall utilization.
So, is it what kind of hardware it support? Like only NVIDIA GPU or other accelerators? Like there are from Hugging Face which support multiple. So they have also a similar kind of framework, NIM Hugs. Yeah. So they support multiple kind of accelerator platforms.
You can download the Hugging Face model, and NIM can work with the Hugging Face model as well as a Hugs will work with the Hugging Face model. So
You said NIM will be able to identify which GPU your node have. Does it work with on-prem or bare metal?
So the deployment doesn't matter. This is more, you can run it on bare metal, you can run it through Docker, you can run it through, yes, GPU detection as well. So for a NIM, if you run it on bare metal, it'll detect the bare metal. If you run it as a pod, like what we showed, then it depends on the GPU operator, how it presents the GPUs to the pod. So it can